we might be able to come up with an easier way of making these things and come up with a way of making them smaller and smaller and smaller and smaller. So this guy, Russell Lowell, figured out that he could make a p-n junction. Then a whole bunch of other people, I mean thousands and thousands of people, started figuring out, boy, we can do all kinds of fancy stuff with this. And in so doing that, all the work that we've already done in making vacuum tube decision makers and processors, we can replace those with these devices, cut the current use down by 99%, 99.99%, and also miniaturize and make them a whole lot smaller. So a radio that used to be that big, that wide, that long, and put out 4 watts and barely fit in the nose of the airplane could now be reduced to a small little bitty package that's about that big by that big that puts out 10 or 15 watts. Okay, and uses 1/100th of the current. Remember I said that vacuum tubes needs a heater grid? A lot of current to keep those things heated up. So we've talked a lot about this. This is kind of a picture of, in this case, phosphorus and boron. So here's straight silica. If we replace an occasional one, note how we've got this extra electron because of boron. And here we're sort of missing one. Well, if we do this right, and maybe every 1,000 or every 100 or every, we then take and bring these together, this electron is going to say, I want to go somewhere. This one's going to say, I'd love to have an electron, but I can't quite. But together, they're going to say, you know what? This is going to happen. It's going to go to there. Okay? That means this side is going to be depleted of one charge, and this side is going to be depleted of one hole. Okay? Polarity-wise, this one's going to be more negative than that. And this is going to be more positive because, remember, the proton equals the same number in here as well. And in truth, it really won't be this electron jumps all the way over to there. It'll go to here. This will dump onto there. This will dump onto there, and on. So I've kind of gone through all of this, so I'm going to kind of move through this. I think the other thing is, so here are some of the doping ranges from 1, say, phosphorus to 100 million phosphorus, or to 100 million silicon atoms, all the way down to 1 per 10,000. Those, I found that spec somewhere. Those tend to be the doping ranges. Now, how they figured out how to do this, let's take a piece of glass and we're just going to move along. Every 10,000 atoms, we're going to go and put another one in. I have no idea. I'm sure it's a chemical process, some type of a chemical, plating or some other process where they cause this to happen. And of course, they managed to figure out how to do that very, very well. However, in doing this, because you can have so many different doping ranges and different doping materials, I can cause P and N junctions that behave very differently, even though they're the same material. Okay, so I could take a P in P device and have 2 junctions, but the doping here isn't the same as the doping here. And in fact, I could say the doping here is pretty heavy and it's a little bit lighter on this side. So I could do a whole bunch of stuff that would then polarize this to where it only gets plugged in one direction. So from the get-go, all transistor devices, when you get to here, we just by default say there's an emitter, there's a collector, and they can't be put in backwards, even though in many cases it would work just fine. All right, so this one, I did a little bit of work to try and find a diagram that sort of showed a slightly offset depletion zone, which it probably does occur. So we're going to say this sort of becomes neutralized, but when I bring these two together, because of the two reciprocal static fields, some of the electrons are going to jump from the N doping to the P doping. That side will then become somewhat positive. This side will become somewhat negative. As an overall piece of material, it's going to be ionized to the negative because it's got extra electrons. The other one's going to be ionized to the positive because it's got fewer electrons relative to the number of protons it has. Okay. Then they have kind of there's all kinds of fancy terms there, but those two will just sort of sit there until I start adding electricity in. And in truth, when I put the leads on, I'm going to put some metal plates there, and there'll be a similar little depletion activity that's going to occur there as well. However, these will can't self-cancel. Okay, as I start adding electrons or holes, polarizing across there, those depletion zones will disappear, and they'll do it equally on either side. So we then have to introduce the idea of forward bias, which says, based upon polarity, if I start creating, adding a bunch of electrons in, where I take the N-type as negatively charging it, and the P-type is positively charged with holes, the depletion zone that I just showed you will get smaller and smaller and smaller, and eventually electrons will start jumping from the N-type material into the P-type material. That will be forward biasing it. Reverse biasing it means to go the opposite direction. Pull a bunch of electrons out of the N-type and then try to shove them into the P-type. That will cause the depletion zone to get bigger and bigger and bigger up until you get to what? There'll be some point, it's still a semiconductor, right? The base silica is still a semiconductor. So there'll be some point where if I keep pulling out of the N and putting them back into the P, it's going to not want to let the current go. It's not going to want to let it go. And there'll be some voltage where suddenly it starts conducting. The lightning bolt starts to go across. We call that the Zener voltage. Okay. Now I can design a circuit or one of these devices, by the way, I dope it, so that when you reach the Zener voltage, it starts letting the current flow, but not in a big, huge cascade. A standard diode, when you do that, you're going to have sort of wound the string really, really tight. So when it unloads and starts conducting, it conducts so much that it shatters the silicon wafer, and the diode breaks. So when I design a diode to break down and reverse bias in a controlled manner, we call it a Zener diode, but in fact, it's truly, that may actually be the next slide. Yeah, it is. Actually, the very next note. So there'll be going to be some point, and this is because of the lightning bolt factor, right? At some point, the insulative quality of the semiconductor, I've got enough voltage potential and reverse bias, but it just says we're going. Depletion zone starts collapsing, doesn't do it well. That's at Zener level. This tends to avalanche once the electrons start. And don't we get that avalanche out in the state of Wisconsin or Nebraska or North Dakota on a nice summer day? Okay, a bunch of electrons get in the cloud, a bunch of holes get in the ground, and pretty soon you reach the Zener value, voltage value of the air, and kapow, the voltage goes. And once it starts to go, things get hot really quickly, which causes the conductivity to go way up or the resistance to go way down, and then and it cascades, and a whole bunch of electrons are going to start going. What typically happens is it cascades in one area. So something that isn't designed to be a good Zener diode, you've got your two junctions here, what'll happen is it'll cascade right in here. So all the current will start trying to go through that one spot. Okay, and it superheats it and causes the thing to explode. And a Zener diode, one that's designed to do that, what we'll do is we'll dope it and play with it some, such that when it starts to conduct, it does it fairly evenly. Okay, and still provides some resistance. Remember we said the diode does provide a little bit of a voltage drop, anywhere from 0.3 to 0.6 volt drop. Well, the same is going to be true if we design it in to make use of its Zener feature. There'll be a little bit of a voltage drop there. Okay. Well, we kind of covered all that. Even when they're on full blast, it's a semiconductor, so it's going to act a little bit like a resistor. It's going to get hot. If I put a lot of current through it, it's going to get really hot. So I might need to put a heat sink in it. I need sometimes to put a heat sink in resistors, right? Okay, well, these are actually diodes here. Yeah, those are diodes. But could easily need to put big heat sinks on a resistor. Big 1 watt resistors, what do they typically come packaged in? Big chunk of ceramic, right? Okay, big chunk of concrete. Allows the concrete to absorb the heat, could increase the surface area, cool off. Well, same thing's going to be true here. These guys, they tend to work a lot cooler if their function is on and off. On and off. Now, while they're on, they are going to get warm. But if they're somewhere between on and off, how do they do that? Don't they do that by increasing the resistance right there? So they become part of the load. So one of these digital devices becomes partially on. It's going to have to get pretty warm to be partially on. So when you use one in an analog manner, you're going to need a much bigger heat sink, as opposed to it's either on or off. The heat sink can be quite a bit smaller. It's also true that heat will affect the behavior of these devices. And it can be inverse, which is not good. Okay, that means as it gets hotter, it conducts more current, or resistance goes down. That's the inverse relationship. So that means if I have 5 or 6 transistors in parallel, and they're handling a fair amount of load, if one of them starts getting hot, its resistance is going to go down. So now more of the current's going to go through the one that's getting hot, which means it's going to get hotter. And you're going to start seeing China syndrome for that one resistor. So one of the things that happens with a lot of these devices is you have to be careful paralleling them in high current situations, and you have to monitor or measure temperature if in fact they are going to operate fairly hot. Okay. Oh yeah, so I already said that. There is, when I somehow I got to hook this up to a wire. There'll be a little depletion zone that sits in here, and a little depletion zone that sits in here. And regardless of which way I bias this, those depletion zones will collapse if I start biasing it. This said, isn't this thing made out of silica? And isn't silica glass somewhat brittle and fragile? Okay, so their biggest weakness is the fact that they're made out of glass and they can break fairly easily. More often than not, they don't break in the middle. More often than not, what we will do is we'll dope the glass with a fair amount of a light metal, like lead or tin or something like that. We'll absorb it into the glass and then solder the pad to it and the lead to it. If it's going to break, that's sort of the weakest structural area. It'll break off right there. And you guys might have seen that in a couple of your rectifiers. That tends to be where the weakest area is. Okay, yeah, that tends to be. Yeah, so then I've talked already about this, so I'm going to kind of go through. Isn't that essentially 2 diodes stuck together? Or I could just get rid of the double P in there. The same thing there for or PNP. So ultimately, if I take a little bit of current, if this sits on the negative side of the load, and I take a little positive into here, these two depletion zones will collapse, and it'll conduct a whole bunch of current for a very small amount of current there, or vice versa on the other one, on the other side. And then I've already talked about all of this several times. So this is a couple of examples. Now this is actually, well, it's an okay. You can use a transistor without this resistor in it or without that resistor in it. But if you do that, then what happens is you lose this threshold area. Okay? So if I don't, we'll do this one. Let's say I lower the resistance in this NPN and I start allowing this to become kind of positive. It becomes positive, depletion zones collapse, the load comes on. Then I bring the resistance up. Well, it may take a while for this thing to start becoming negative because there's no place for the negative to go here. Now, if I take this directly connected to negative, it's going to stay negative when I start to open this up. So typically, I'm going to make this quite a bit higher resistor. Let's say if this is 0 to 1.5K, this might be 10 or 15K. Okay, but once this thing starts to go back up, this will start going negative through there. It's a positive shutoff for the transistor. Same thing true here. Once the resistance goes up here, this causes the in here to go positive, shutting it off. So again, I've kind of talked about the upper one on emitter and collector. So it's important to note that transistors get used like a potentiometer, variable voltage out or variable current out, or they get used like a switch, high, low, on, off. And different strategies of doping and design of the transistor make them better for digital or better for analog. Okay. So it's not uncommon to see a schematic diagram where you might see VCC and VEE and a variety of inputs, a grounding input or a powered up input going in, maybe some digital inputs going on. They don't really tell you what the major magic is in here. But then they'll say, okay, I've got a load. Let's say this is your fuel ejector. Okay, that load is controlled by the transistor, and they'll show this part of the circuit so that you know that you should have positive here, negative there. You should feel the primary voltage drop across there, and from here to ground, a very small voltage drop while it's on, very high while it's off, etc. Okay? You're never going to be able to diagnose this in most cases. But you can assure that you've got VCC. You can assure that you've got ground. And you can assure that your inputs are doing the data they're supposed to be doing. And if they are, you can then come over here and say, is the controller controlling the load appropriately? Well, yeah, it's controlling the load appropriately. Well, maybe the load's the problem. Okay? Or no, it's not controlling the load appropriately. Input's good, not working here, good. Then the major magic isn't magic anymore, right? So by process of elimination. The truth, once you get comfortable with that, computerized technology is actually a lot easier to diagnose. Okay, you undo one connector, put a pin-out board, and hook it back up, and then you just start sampling. And it's a much easier way, much easier to diagnose problems. The less it's intermittent. Okay, so it turns out that we can make a whole bunch of different kinds of these devices that react to light, that react to heat, that react to magnetism, the Hall effect. Okay, that react to gravity or strain, okay, piezoelectric. We can come up with a bunch of different types, like an op amp that will compare two voltages and make a decision. Okay, if the voltage is here, my output's going to be there. Or if the input is here, my output's going to be there. Or if this voltage, the low voltage, is this close to the high voltage, my output's going to change state. Or I could take the output and feed it back in and use that as a gain to create a gain, right? I could use one that would create timing data. Do all kinds of different fancy stuff. Common to most packages of these integrated circuits is the input leads will have very high impedance. This means it's hard to damage its little brains. Okay, it's very sensitive. It doesn't, it can measure a high state or a low state or some analog value of voltage without any current. I mean, just the smallest amount of microamps. It doesn't need much current to be able to measure it. That's good. That means if suddenly big voltage surge happens or something else happens, it's got very high input impedance. Yeah, so what? Oh, everything went up to 20,000 volts. Oh, well, no big deal. The resistance was so high, it just disregarded it. Okay. It's very, very common for the outputs in these devices to be electrically isolated from everything else. So the main power that comes in goes off and does all of this, and it's separated and goes off and drives the output devices. But the output devices themselves, other than what's controlling them, are completely electrically isolated from the rest of the circuit. Therefore, if an output does something weird, it doesn't affect the controller at all. So let's say it's a starter. The output is to turn on a starter. Well, if it's correctly isolated, then that starter, 300 amps coming on and going off and all that inductive surge happening, it just says, okay, doesn't hurt us. It will always, they'll use some term for V plus, VCC, VE, VG, something like that for power and ground. And these sometimes, or fairly often actually, aren't shown in the schematics. It's also very common to make these things in preferred packages. So like an op amp, it's actually hard to buy a single op amp. You can buy a quad amp very cheaply. Okay, and you just only use one of them, right? Only, okay, we talked about gain already, so I'm going to move past that. It's important to note that with respect to inputs and outputs, this is kind of where you got to do a little bit of homework. What is the input on a data line going in? Is it analog? If it's analog, what am I looking for? Okay. Oftentimes, if it's analog, what will happen is the input will be some type of a resistive element, like a sensor, right? And that value will vary. So what's going to happen is the computer will feed a reference voltage, like 5 volts, out across a very high impedance. So if the resistor here is at high resistance, then the voltage, line voltage, will be 5 volts. And on the input side, it'll say I'm getting 5 volts. If the resistance value of the sensor is low, then it'll drop all the way down to maybe, 0.3 or 0.2 volts. And the computer will say, okay, I've got very low voltage. Or somewhere in between, right? Now, we don't know what that sensor is. It's very, very common, though, in analog to see something like that. Say, call it 0.5 volts to 12 volts, or 0.4 or 3 volts to 5 volts. Whatever, that's the value the computer is actually seeing. Then its program says, okay, based on that voltage, I'm going to feed that to an analog to digital converter, come out with a hard number, and then that number means display up on the gauge that I've got 82 psi oil pressure. Okay, if that's what the sensor was. Okay. And then, of course, output could be anything. What you're seeing on the screen is an output. Unlimited. You could have interlinking between operational systems. So, for example, let's use an oxygen sensor and a fuel injector on an engine. Okay, the computer's getting data from the oxygen sensor. As the voltage goes up, it's saying the engine's going a little bit rich. It then says, okay, we're going a little bit rich, so it backs off a little bit the amount of time that the injector is on. Okay, so it's backing it off. Well, it takes a while for that combustion event to get converted into exhaust, to get down to the oxygen sensor, and cause the oxygen sensor to start dropping down. However, the input that the oxygen sensor gave caused an interlinked reaction to the injection time, which ultimately caused the oxygen sensor to start going the other direction. So now you have this sort of hunting behavior, whereas the injector on time is changing, sort of out of sync with the oxygen sensor. Okay, that kind of interlinking can also happen diagnostically. Now, in the case of oxygen sensors, because there's so much delay, we came up with some terminology for it called O2 trim, and there's an expectation that you'll get a little bit of this. That's one example. Another example would be a very badly designed, just off-on switch for light and dark. Okay, it gets dark out. The switch says it's dark out. Okay, turn the light on. The light comes on. The switch says, oh, it's light out. Turns itself off again. Right? That would not be functional. Okay, but you know, I've seen that done. Actually, the hangar out at Montgomery Field, the district went out and reinstalled a bunch of stuff to automate that light, and it's like, guys, you do know when the light comes on, the sensor's right there, it's going to turn off. Of course, there was enough of a delay, so it would come on for about 10 minutes, and then it'd say, okay, click and go off again. Not a lot of rocket science there. So here's an example of an operational amplifier, and this is actually only showing one element of the operational amplifier. We can actually have a number of other components in there. This shows its decision-making capability. This is what's actually in there. Okay, all those little transistors, resistors, some capacitors, and ultimately what it's going to say is, I'm going to have a high and a low, and depending on what I do with that high and the low, my output is going to go either high or low. Also note that in this case, here's the power for it, and there's the ground for it. And this symbology that they use negative VCC to determine whatever reference ground is. And if you go on to move into electronics, this is going to be one of your basic devices right here. The op amp is used to create a gain. It's used as a buffer. It's used as an and/or. So this is an example of a flip-flop latch where what we're going to do is we're going to say, depending, and it's doing it, okay, if I flip this, the state goes that way. If I flip that, the state flips to go that way. Okay, if I activate that one, the state flips to turn that one on. And if you look over here, what's going to happen is, if I latch this one, I'm going to turn that one on, which is going to then shut this one off. Then if I latch the other one, that's going to turn this one on, which will in effect turn that one off. So, you know, I don't know, I could use that for maybe left turn signal and right turn signal. I don't know. That's just one example of a logic circuit that's designed to do something specialized. Um, it's also important to note that this device is a memory device. Okay, if I don't do anything, don't I know that I've said, if I didn't do anything here, I'd say that's high, that's low. As long as I don't do anything, that's high, that's low. Okay, I've got 2 bits in my binary. If I hit here, it'll switch. If I hit here again, it doesn't do anything. Okay, so it becomes a memory spot. So that's one way of doing it. There's another type of latching device right there. So the latches are going to be the 1 or the 2. Another kind of useful device is called a 555 timer, or if it's a 556 timer, they'll have 16 pins and they'll put 2 timers into one package. But in this particular unit, what we're going to do is we're going to have a couple of op amps, NPN transistor, some resistors, the flip-flop latch that we talked about, and this actually the output driver acts as a buffer. But if I put this into a circuit, let's say I've got an LED, I can cause the output 3 to go high versus low versus high versus low, and depending on which way I've got these LEDs wired in here, I can switch which LED comes on. The way I'm going to set it up and work it is, I'm going to turn the switch on, and I'm going to let this capacitor charge up. Once this capacitor charges up above a certain value, the threshold, number 6, is going to say, as well as the trigger, are both going to say, we've reached the voltage value. Latch, boom. And when they do, they're going to open number 7 right here, which is going to be your discharge. Notice how this is about half of that. Now what's going to happen is the capacitor is going to discharge to ground, so it's going to go back to low. And as it discharges, it's going to discharge at the rate that it's allowed to go through here. And then it's going to recharge at the rate it's allowed to go back through there. Okay? Based on those resistances and the amount of capacitance there, that will determine the amount of off time and the amount of on time. Okay? So that's just a basic timer circuit. What would you use a timer circuit for? How about intermittent wiper duty? Okay, if I want to be able to rotate a knob and have the wiper come on every 5 seconds all the way up to every 20 seconds, okay, what I might do is I might say, let's design this circuit. We'll make this be a variable resistor. So we'll change how much off time can occur. But the on time will remain the same. Then this will come out to a small, since it can't handle a lot of current, we'll bring this out to a small relay and activate the relay. The relay will come on for 3/4 of a second. All it needs to do is turn the wiper motor on enough to where its internal switching gets the wipers out of park. Once they're out of park, they'll go through a full cycle, come back and repark themselves. Okay? So now all I have to do is take my variable resistor and make that the knob that I use to adjust how much time between wiper intervals. Right? Well, that's one example of a timing device. They have a whole bunch of different kinds of these that are quite a bit more stable. The downside of this type of circuit is over time resistors do change a little bit, but more importantly capacitors change over years. The dielectric begins to break down, and they don't have as good a charge as they do. This thing also has, because of the output driver, it will also control some things. As this is going on and off, there may be an inductive pulse. By having coming out of 5, you've got the control voltage here off of that capacitor. This guy can suppress any spikes that are happening out there. You can do a number of things This is one of the earlier integrated packages that's been around since, I'm going to say, the early 60s. Okay, these guys are cool. And this is sort of the wave of the future. An Arduino Mega 2560 is a programmable controller commonly used in 3D printers, CNC mills, other robotic devices. And you'll see, whoa, it's got a whole bunch of stuff going on there. Well, in truth, you're going to have a whole bunch of inputs and a whole bunch of outputs. They're going to make a whole variety of different things there so that the chip manufacturer can sell it to a whole bunch of different manufacturers. In fact, these guys, the way these are set up is these are sort of practice devices. This whole setup actually sits on that board with a bunch of header pins that you can then hook up whichever way you want, and then you can write a computer program that goes in there. Okay? What the computer program can do is it can say, all right, we're going to take data, and I'm trying to remember, data in can be this one over here. I think it's this one right here. I can do data in. Here's all your VCCs and all your grounds. This one right here can be data swinging in from the computer. So I can say in my computer, I use my CAD CAM, and I designed this nice wide angle thunder bearing. Okay, and it's going to be nice and milled. So through that, I'm going to go through a set of programs that are then going to translate the object into a series of actions by the mill head. It's then going to translate that into what's called G code, which is standard automation code for many CNC operations. That G code will then transmit to this guy, and it's going to take the G code and then translate that into driving its outputs to the servos. Okay, so it'll say, you know, for the 3 or 4 or 5 servos, here's what I want you to do. I want you to move X number of turns and parts of a turn at this time. Well, these guys are kind of fun. I actually took a smaller version of one of these. There's another company, there's a Parallax that makes some real simple test ones. I went through and hooked up, got a 3-axis TI, actually I got them to send it to me for free, accelerometer. What I was trying to do was make a little meter. I didn't really care about the display. That was kind of cool. I made the display that would provide G data, gravity data. I didn't really care about the display. What I wanted it to do is to put out a tone. So the more G's you put on the plane by pulling the stick back, the higher the tone would go. And the negative, it gave a slightly off-shifted tone. So you went negative G. So then when you went through a loop, you could go back down. And use the tone to cause the loop to be totally coordinated. It ended up working. I had a lot of fun with it. And just, again, an experiment. But programmable controller, an input chip, did a little bit of programming. So in today's world, everything's made out of these devices. This was just one example. So the upside of these guys is pretty straightforward. Really easy for troubleshooting. Do you have the proper ground and do you have the proper power while the circuit is running and loaded? Okay, how do you check for that? Standard voltage drop, right? Okay, are all the connections correct? Did something come disconnected, or you disconnect it and there's a bent pin or something like that, right? Then check all your inputs. You might need a breadboard or a pinout box, something like that. Check to see that all the data going in is correct. You might have to do a little bit of homework to get known good data. If all the input signals are correct, then verify that all the outputs are correct. The output signals are correct, then you've either got a failed load, okay, whatever it's actuating is a problem, or if you've got intermittent issues, you're going to have to keep operating it until it's starting to fail, then test it. Okay, so, but that that diagram right there is the appropriate diagnostic troubleshooting chart for anything computerized. Pretty straightforward. All right. Let's start talking about avionics. This is sort of a big segment. And this will sort of, when we get into antenna and wave propagation and all the rest of the stuff, this will cause your head to hurt a little.
More?
No, our head hasn't hurt yet. Our head's going to hurt now. And I'm just barely scratching the surface.
You're going to talk about ground planes and all that kind of good stuff?
And a little bit, but not much. All right, avionics. This pun intended, the sky's the limit. And the more we go, two things are going to happen. The more weird, cool, fancy stuff is going to be available, and the faster it's going to come at us. Okay? So the learning curve for us is really, really severe in this realm. So we got to start talking about, before we start talking about radio theory, we're going to come up with an analogy. We're going to use sound transmission. Sound transmission, sound travels to you. We've got a bunch of air here. And when my voice box does some stuff, it's going to cause compression and rarefication in an oscillatory manner. Okay? The frequency of that oscillation is going to cause a change in tone for you. The magnitude of the oscillation is going to cause it to seem loud or soft. Okay, so how much it's pounding back and forth, okay, is going to be loud or soft. How fast? Okay. So, intensity is going to be a function of both. So really loud at high frequency is going to be more intense. Okay. Now, the other thing that can happen is the frequency of what's coming at you is a function of me standing here and you standing there. And it's going rarefication, compression, rarefication, compression, rarefication, compression. However, as I start walking away, we now have to subtract the speed of me walking away. In fact, you didn't realize, but as I'm walking towards you, because I'm getting closer and increasing the frequency, what you're hearing from me, it actually went up just a little bit. Probably weren't able to hear it. But in something fairly high frequency, like an ambulance going by, it goes higher and higher and higher because the frequency is going up, and then there's a shift and it starts going lower and lower and lower and lower as it's going away from you. Okay? So that's Doppler effect, because the relative speed between the listener and the sound maker, or the transmitter and the receiver, changes depending on where they are. Okay? Within the speed of sound, it travels at approximately some value at sea level, at a standard day, blah, blah, blah. If I go up in altitude, it changes. If I change the pressure, change the temperature, all of these vary. Also, if I change the density of the material. Okay? Because isn't that what's really happening when I go up or down? In fact, the speed of sound doesn't change much with changes in pressure. It's almost entirely temperature dependent. Okay? If you know, in other words, if you know what the temperature is, you can calculate the speed of sound for any condition. Okay? So, yeah, it's a lot faster in liquid. However, liquids are a lot denser, therefore the amplitude or the intensity of the sound wave is going to decay quite a bit quicker. Because remember, as I compress and rarefy, I'm making molecules move back and forth. Well, how far can they do that? Unless I'm really, really loud, that energy is going to continue to decline. That's why sometimes when you hear a loud bang and it's from really, really far away, like a lightning bolt, kablam, only it's, 15 seconds away, and you hear it, and it's 15 seconds away, that's 8, 9 miles away, it's a long ways away. It made that much noise, that much energy transmitting out in every direction. Not only this way, but upwards. Okay? You just heard the one little bit of rarefication and compression that happened to hit your ears, but all that energy went all the way out all the other directions. Of course, now take that to the example of the big rock band out on stage, okay? And you can hear that bass drum going boom, boom, boom from 5 miles away. Only there's a concert thing that's out by Oshkosh. I'll set my tent at Oshkosh 5 miles away, and I can see the fabric of my tent going boom, 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 boom. From 5 miles away, they're actually able to move the fabric of the tent. Can you imagine what's happening to those fools that are up close to those speakers, drunk out of their mind? Okay, their eardrums are meeting inside somewhere. I just like, oh my Lord. Okay, for humans, if you're not too deaf, you can hear all the way down to about 20 cycles per second, all the way up through about 20,000 cycles per second. If you're my wife, you can hear any hertz whatsoever, okay? Because at the end of the day, it's me that's going to hurt, right? Yeah. Oh, it's amazing what that woman can hear. Okay. So I can do the same thing with the electromagnetic ethos that exists everywhere. I don't need atmosphere. This is in all of space. Okay? And in fact, the less matter there is, the better this will work. If I have to do this through matter, it somewhat interferes with that electromagnetic pulse. But I can do this, I can create that rarefication and compression in the electromagnetic and electrostatic fields and cause propagation that will occur in a specific direction or in a very uniform sort of unilateral direction. So I could be out in outer space, not near anything, and send the pulses, rarefication, and compression out in all directions. If I happen to be on the surface of the planet, it's not going to work downwards. Well, that's the same as if I'm standing on the edge by the beach, right? And I yell and scream. It goes out over the water, but it doesn't really go down into the water that well, right? Well, same thing will be true here. It turns out that if I take a couple of leads sticking out, my arms are the two leads, and I go negative, negative, positive, 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 and then flip it around and go positive, 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 negative, negative, negative. What I'll do is I'll create two electromagnetic pulses, electromagnetic pulse based on the current flowing, and an electrostatic pulse based upon the voltage flowing. Okay, or voltage occurring. So those are going to occur exactly opposite directions from each other, and they're going to come out at right angles to each other. So I'll show you some pictures of that here in a little bit. This gets a little confusing. So if I go from really, really positive and really, really negative all the way to the point that this is really, really positive, this is really, really negative, all the way back to the point that this is really, really positive and this is really, really negative, that's one full cycle. Okay, so that's one full wave. And if I get a propagation off of that, let's say I've got a propagation here, it will be represented by one full wave coming off of there. That wave will have some distance. Okay, so not only can I measure it in units of time, but I can also measure it in units of distance. How fast is it going to go? It's going to go at the speed of light, but that's still a finite measurable thing, right? Okay, so if I'm compressing and rarefying on a 1 second cycle, That's going to be a very significant wave, very slow frequency. It's going to go, and it's going to tend to want to go a long, long way. And if I think about a rope, if I go really, really fast on the rope, the impulses are going to be really short, and they're not going to go very far, are they? Right? But if I take the rope and go whoosh, 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 okay, a lot of slow motion. Now the cycles are going to go a lot further. It's going to take more energy to do it, but they're going to go a lot further. Okay, so this is a little hard to kind of quantify. But if I take my rods and put them out here, what's going to happen is I'm going to have my voltage ripple and my magnetic ripple are going to occur at 90 degrees from each other. Okay? They will decay in amplitude. They don't actually decay that much in frequency. They do a little, but they don't decay that much in frequency. They have to a little bit. In fact, that's what we do to make GPS work. But part of what we do to make GPS work. But what will cause them to decay is if I'm going to or away from the object at some significant speed. Now, since this is happening at the speed of light, the rate of travel in my car relative to the speed of light isn't going to cause the radio to sound slightly higher frequency than slightly lower frequency when I turned away from the radio station. They are different though, right? So current pulsing will be, or in this case, we're saying voltage is one direction, current is at 90 degrees, the other direction, all right. So again, they travel at the speed of light. That's pretty fast. So that's not the frequency, but that's just the distance. If I take away and go whoa once, it's going to propagate at the speed of light outwards. If it hits any kind of matter, like the atmosphere, or the ground, the water, or anything else that will cause it to slow down, it can also cause it to reflect. Okay? And in fact, I can use matter to reflect part of the signal, or I can use the ionosphere to, which is sort of compressed matter, to create a reflection. Instead of the energy being lost way up there, it'll actually bounce back and forth around the planet. Okay? So then if I vary the amplitude or the frequency, I can use this to transmit data in a variety of different ways. It used to be we just used a straight carrier wave, varied the frequency slightly or the amplitude. We've now discovered that we can use that same carrier wave, but use it in a semi-square form at a very high frequency and send digital data instead, and then translate that digital data back into whatever we need. Ones and zeros, a picture, audio, a video, whatever you want. Okay? So it's fair to say, or true to say, that an electromagnetic pulse will travel through anything. It's just going to take more energy to drive it through lead than it is through nitrogen. It's going to have how do I want to say this? Here's the way to say it. If you're speaking to me, you're making noise, there's a sound source there. If I turn this ear to that sound source, okay, that compression and rarefication is happening this way, coming to me. I'll hear it louder, okay? Versus if I go this way, I won't hear it as loud, right? Okay, in this particular case, the compression and rarefication are coming this way. If I took and made a ripple on the ocean, if I was on the edge of the ocean, I'd see the ripple coming like this, is up and down, and I'd see that real well. But if I was straight over the top of it, I might see the circles, but I wouldn't necessarily be getting that, receiving that data, because I'm at a polarization that doesn't allow the data to actually get to me. And it's probably even easier to say, if I'm down underneath it, it would be even harder to see it, right? But if I'm right on the edge of it, I'm going to get the energy of the waves going up and down as they hit me, okay? So the same thing is going to be true here. How I'm oriented to the direction of the waves, so and particularly given that those waves moving up and down me, let's say I'm the rod, those waves going up and down me have to induce electrical flow inside me. So if it's moving up and down me, it would induce electrical flow inside me. But if I was turned 90 degrees and it was moving up and down, it wouldn't really induce much, okay? And the same thing is true outward. So it turns out that because this orientation really matters, what we've done is we have said, all right, so with respect to communication, primarily communication, which is also going to include non-directional beacon, we're going to take and put the axis of motion on the vertical. So we're going to orient our antennas on the vertical, and the wave action that's going to come out of those are going to be on the vertical. With respect to navigational, more often what's happening is the surface is here, and I'm somewhere around here, and I want to know where I'm at. So in that particular case, I'm going to instead cause my wave action to go back and forth this way, or horizontal, which means I'm going to orient my antennas on the horizontal. Okay, so wave orientation can be is very critical. But also note, so far I've sort of been talking about a single antenna output, okay, pole going down and a pole going up, that's radiating out in all directions, omnidirectional in all directions. I can shape this so that it focuses more energy in one direction. I think I'll talk about this here eventually. All right, so this is a little hard to describe, but if I start polarizing things, in this case it looks like I took and made this really positive and that really negative. I brought the current up, this became very positive, this became very negative, and it created a significant electrostatic field between those two, okay? And then as I start reducing their amount of voltage, what's going to happen is this is going to start getting smaller and smaller and smaller, and it'll come down to the point that it just it makes a circle that drops off. Okay, then it's going to go back up, and so my wave propagation in this particular case is going to be this circle going out all the way to a tight circle, to a big, to a tight circle, to a big, or compression and rarefication heading outwards. Now, meanwhile, when I take this and go from negative, it's negative, positive, and I flip-flop it quickly to positive, negative, the opposite direction, when I'm halfway through, my current's going to be maximum in the middle here. Okay? But my magnetic field, instead of being this way for the static field, it's going to be circular around it because of the left-hand rule. Okay? So my magnetic propagation is going to be that direction, or 90 degrees off. So it's the wave orientation is always going to be a function of the electrostatic field. That's not to say that the magnetic isn't propagating, but we define orientation relative to what the electrostatic field forms. Yeah, pick one. So in this particular case, I'm going to take a vertically polarized wire, and in truth, it's going to be two individual wires. And I'm going to say positive, negative, negative, positive, positive, negative, back and forth. And I'm going to create these waves, electrostatic waves, that are polarized this way, and the magnetic wave is going to be polarizing this way. Well, the data that's going to be important to me is the electrostatic field that's coming out, and the receiving antenna is going to also be oriented. If I turn it 90 degrees, it's not going to be receiving the electrostatic field. It will receive the magnetic field, but that's not useful to me.
So the carrier's magnetic field is it what that?
No. The carrier is both.
It's both?
The carrier is simply the up and down. Okay, so the carrier says, if I just go DC, I get a pulse and that's it. One pulse, that's it.
Mm-hmm.
So for me to be able to send data, I'm going to have to go back and forth. I have no choice. I have to polarize and reverse polarize and reverse polarize and reverse polarize and reverse polarize. So given the construct that I have to reverse the polarity again and again and again, the only way to actually transmit data is to change how fast I reverse the polarity. Faster, slower, faster, slower, faster, slower, or frequency variation, or the amplitude, or some combination of both. Now, until we figured out that we could use each one of these to represent a high and a low, and we started transmitting digital data, which could be used to do anything, to have any meaning, that was sort of what we were limited with, because you've got that, along the surface of the water, you've got to have ripples happening all the time. So I can ripple faster for high tones and ripple slower for low tone, and ripple faster for high tone, so that would be frequency variation. Or I could hit real hard for high tones and real soft for low tones. Okay? How hard for high tone? That would be amplitude modulation. Okay, or AM. So then in this particular case, now what's going to happen is if I orient the antenna on the horizontal, now my electrostatic field is going to be on the horizontal, and I need my receiving antenna on the horizontal. So it's the electrostatic field that will transmit, how do I want to say, both of these will be transmitted, but it's the electrostatic field on the receiving end that will induce a voltage signal that starts going back and forth in synchronization with that one, that I can then take that data, pull it out, amplify it, filter out the carrier, and then whatever data is left over, use that to tell the tower controller that I think he's a big twit, and he should let me land whenever I want to. So it turns out there's a whole bunch of different frequencies. Okay? There's a whole bunch of frequencies. We can say here about the size of a football field, we're talking about 100 meters. I can make a wavelength that's about 100 meters long. Okay? Very slow wavelength. Electromagnetic spectrum. As I start getting shorter or higher frequency, now I'm getting to maybe the size of a bee, then to a pinhead, and I'm getting faster and faster. Now we're down to the size of a regular cell, bacteria even smaller, even virus. Well, right about in this electromagnetic frequency, you have visible light. Okay, so the photons that are actuating in that frequency range, that little narrow frequency range, that's everything you can see. Then we start getting, infrared to ultraviolet. Here we start getting into X-rays, and then there we start getting into, and the distance between points here is the size of an atom. Okay, the length of the frequency. Here, the length of the frequency up in the gamma spectrum is the size of the nucleus of an atom. How small is an atom? I heard one the other day, I don't know how accurate it is, but if you took the distance of an atom across an atom and kept doubling it, each time you doubled it, okay, doubled it and doubled it and doubled it and doubled it, at some point you'd get to the size of the planet Earth, right? Atom, planet Earth. The halfway point is a microscopic dust speck. Okay, something that you can't quite see with the human eye. That would be the halfway point. So take a small dust particle that you can barely see with the human eye and double it until it's as big as planet Earth. That number of steps go the other direction. That's how small an atom is. Again, you got to come up with ways to sort of mentally visualize this, because, all right, so electromagnetic spectrum. We'll stop on this in the next slide. So because of all of this range, we said, you know what? Let's sort of take this out here, about in here, we're going to say, let's reserve it. Because everybody wants to communicate. They want to use this radio and talk. Okay? Play their country music. Right? Everybody wants to use it. So we're going to have to come up with some way of dividing all of this up. So what we're going to do is we're going to create groups of wavelengths. So from 10 meters down to 2 meters in wavelength, we're going to call that this group, and we're going to call it a band. Right? And really, if you look at that chart, it's a band of that one segment. Okay? Then what we'll do is we're going to say, for this band, we're going to designate it to this use. So for the use of all airplanes, we're going to say from 108 megahertz, or million cycles per second, all the way up to 137 million cycles per second. That's dedicated to aviation. Okay, that's actually a fairly narrow, little bitty part of the total spectrum. We're going to reserve some for the police forces and the Secret Service and television and radio and cell phones. And cell phones. And cell phones. And, man, everybody's got to have one of these. And cell phones. Right? Okay, so we're going to keep having to add stuff. Well, then what's going to happen is we figured out, this technology that we used to make is kind of sucky. So we figured out that now that it's a little bit better quality, within these bands, it used to be we'd only listen to maybe 24 channels. Okay? But if you get the two too close to each other, they start bleeding into each other. But it turns out if we get better and better transmitters and receivers, we can now fit 36 channels in between. Well, that happened in aviation. For years, we only had 360 channels within that 108 to 135. Okay? We were able to double that by getting better transmitters and better receivers. We actually developed it a long time ago, but it took a while for everybody to buy all this equipment. So we went to 720 channels, individual different channels. However, then we said, you know what? Because other frequencies near us also got better, we've now got a gap in there that we're going to, so we actually went from 135 to 136. So we went from 720 up to 760. Okay? That's why you'll see it's a 720 channel radio, 720, okay? So a channel is some range of frequencies, say 108.001 to 108.02, or man, not even that, 0.01505. That range of frequency is one channel. Then I'm going to need a little bit of gap for the next channel. And I'm going to go 108.007 all the way up to 108.010 or whatever, 11. Okay, so I'm gonna have to have a little bit of gap between these so that the transmitter and receiver, as I go in a range across that frequency a little bit because of Doppler effect and everything else, I don't bleed into the next channel. And even that, as I start reflecting and other things happen, and this happens oftentimes. You guys may have heard this occasionally, even with radio transmitters. You'll occasionally hear a different station for a little while, or slightly hear a different station, particularly if you're already getting it, it's a little bit weak, and suddenly you start hearing another one, and then back to that one. That's because somewhere it's reflecting, and Doppler effect is slightly shifting the frequency off, just a little. Okay, so you need some separation between channels. Okay, a group of channels devoted to, okay, or a group of frequencies devoted to one use will then be called a band. And then we'll assign all these different bands to various different uses. There you go, guys. Your head hurt? Oh my Lord, I can't even begin to read all of this, right? So aviation is this little blip right here. Okay, and that's all of aviation. That includes military and several other things as well. So we get this little bitty blip. Okay, man, howdy. It's just, it's kind of a mess, huh? And in fact, and you can see there's a bunch of shared different duties going on as well. Now it turns out that straight, how do I want to say this? Straight data, analog data, doesn't actually work that well at higher frequencies. You really have to use it at a fairly low. So the AM band, and the AM band actually, which includes us in aviation, is actually fairly low on the spectrum. The FM band actually operates within the same amplitude of the AM band. How do I want to say this? The AM band sits at, I don't remember, but the AM band actually fits within one of the frequencies, reserved frequencies within FM that's used for amplitude modulation. So all your AM radio stations sit on one frequency, but they change with amplitude modulation, and then frequency modulation sits on either side of that. But that's also a fairly small window, and I don't remember where it is. It's down here somewhere in here. It's one of these smaller windows. Everything we do for navigation and communication occurs in that little band. All kinds of different stuff. Okay? That is the radio spectrum, and you can look it up.
Is that so we can talk to other countries? Is this kind of a universally adopted?
No. You think Fidel's going to agree to doing?
Well, the Euro countries.
Yeah, maybe. Parts of it, yes. Parts of it, no.
I don't know if it does. Complicated.
My guess is corporate agreement, like from Verizon across the board, or Sprint or whoever, probably does more to influence good behavior or standardizing behavior than international law does. Now, my guess is there's probably some reasonable standardization where they want to do business in adjacent areas. I would also say, because we invented all this, in all likelihood, it was easy to sort of copy what we've been doing. So the basics of it probably is copied by most. But then when, the U.S. makes a bunch of haggling between USNet and Verizon and IBM, and they do a bunch of haggling up in here somewhere and making some backroom deals, well, Mexico doesn't care. Okay, they got nothing that's operating up here, right? Okay, so let's break here. What did I do? I ran about 10